Section 9.3, Testing mu when sigma is unknown. So in this section we're going to switch from doing tests on population proportions to population means, and we want to look at what the changes are that happen with that. And there's two key changes. One of them is we get a different formula for our test statistic, and that in turn changes how we get our p-values. So let me remind you about what we did in section 9.2. So in 9.2 our test statistic was a z-score, and we took our sample proportion p hat, we subtracted the claim proportion p0, and we divided by the standard deviation of p hat, which would be the square root of pq over n, but we didn't know the values of p and q, so we substituted the claim value p0 and q0 over n, and that was our z-score. So we'd like to do something similar here in section 9.3. So instead of the sample proportion, we're going to do a sample mean. Instead of the claim proportion, we're going to do the claim mean. And just like this was supposed to be the standard deviation of p hat, down here we would like to put the standard deviation of x bar. You might remember from section 7.3 and 4 that would be sigma over root n. But we aren't going to know sigma, so what we're going to do instead is put s in its place and use s over root n for the standard deviation of x bar. But because it's supposed to be sigma, instead of getting a z-score, this change to s is going to give us a t-score. And that's the same thing that happened with confidence intervals, where we made the substitution of s and ended up using a t-score. So that's very similar. And then when we go to use go to find our p-value, because we have a t-score, instead of using normal CDF, we're going to use t-CDF, and I'll show you how that works with these next couple examples. So since the changes here are primarily mechanical, I want to start off with a couple examples that don't have any application to them, but just the mechanics. And then after we practice that, we'll move on to applications. So for each of the following, we want to determine the test statistic, the p-value, and then decide whether or not we should reject H0. So they've already done a lot of the setup for us. They've come up with the H0 and the H1. They've decided on a significance level alpha, and that's our setup phase. And then they've started the gather and weigh the evidence phase in that they've got an x bar, an s, and an n, but we want to turn that into a t-score. So we're going to finish that step off and see what the mechanics of that looks like. So t is x bar 5.113 minus the claim mean, which comes from H0, so that would be the 5.2. And again, we'd love to divide by sigma over root n and do a z-score, but we don't know sigma, so we'll use s instead, 0.8991. And then we're going to divide that by the square root of n, which is given as 123. And the purpose of the test statistic, just like in the last section, is trying to determine if our x bar is just a small difference away from the claim value, where the claim value could be true and that difference is just due to random variation. Or is it a big difference that couldn't be random variation, or at least is unlikely to be random variation, and makes us think that this claim value is incorrect? So let's see how far apart those are by computing the test statistic. Now when you go to do that on the calculator, we have two numbers in the numerator, so you want to put parentheses around that, and you have two numbers in the denominator, so you want to put parentheses around that also. So let's go ahead and see what that looks like on the calculator. So we have 5.113 minus 5.2 divided by, so parentheses around the top, now open parentheses for the denominator, 0.8991, and divided by the square root of 123, and then end the parentheses for the denominator. So I get a test statistic of negative 1.073. And in my mind, that mostly decides the hypothesis test, because that's saying that my x bar is just about one standard deviation away from the claim value, and that's pretty close. And so that's a small enough difference, I think it could easily be that HO is true, and I would get an x bar like this just due to random variation. So when I say that could easily be the case, we should calculate the probability that that could be the case. So suppose that HO was true, then if we had a normal curve for this, we could put the 5.2 in the middle, but instead we'll put the t-score for that, which would be 0. And then we would put on our test statistic of negative 1.073. And at this point I would like to shade, but I need to think about, is it left-tailed, right-tailed, or two-tailed? There's a tendency sometimes to think if our test statistic's on the left that it's left-tailed, but the tailness of our test is not decided based on where our test statistic lands, but based on what H1 says. Since H1 says does not equals, this is a two-tailed test, so I have to put my test statistic on, but also the mirror image of that test statistic on the other side, and then the p-value in a two-tailed test is both the area to the right of the positive value and the area to the left of the negative value. Now, by symmetry, those are both the same, so it doesn't matter which one we find. It's often a little bit easier for people to find the one on the right, so I'll go ahead and do that. This is a t-curve, so I want to use TCDF to find that area, and that goes from 1.073 to infinity. But on a t-curve, you have one extra number you need to put in, and that's the degrees of freedom. And so with a t-curve, the df is n minus 1. So our df here would be n minus 1, which in this case is 123 minus 1, or 122. So I'll just put that number on there as well, and then I'm going to go find that on the calculator. And TCDF is just like normal CDF, it's in the distribution menu, so above your variables key here. So I'm going to hit second and distribution, and we see TCDF number 6 on this calculator. It might be different on yours depending on whether you have a TI 83, 84, and so on. And I'm going to put the left boundary, 1.073, the right boundary, which is infinity, and then 122 degrees of freedom. And I get the area to the right of that value is 0.14. It's a 26, but that 9 would round that up, so that would be 1427. So that's not actually my p-value. The p-value is the area of these two together. So the p-value for this test statistic, or for this test, would be 2 times 0.1427. And when I double that, I get 0.2854. So that's my p-value, and at this point we finished with that gather and weigh the evidence, and it's time to make a decision. And we want to decide, should we reject or not reject HO based on this evidence. And in some sense we always want to reject HO because we're kind of trying to prove H1, so in some sense we'd like that one to win. So we want to reject HO, but before we do that we always weigh the risk. What's the risk I'd be making a type 1 error if I did reject HO? And in this case that comes up as 28.54%, and I'm only willing to take a 5% risk. So this is almost 6 times more risk than I'm willing to take of making a type 1 error. And that would be the error if I decided to reject HO. Because that risk is too high, I'm going to avoid that risk and say do not reject HO. And my reasoning would be that it would be too risky to do that. Normally we would go on and do step 6, but step 6 is to talk about this in words of the application, and we don't know what this application was, so I'll leave it there. So I just talked about this in terms of risk. Let me just say it one other way in terms of the random variation. When we see that we get this test statistic of 5.113, we're trying to give this claim value H0 the benefit of the doubt. Maybe it's true. But if it's true, could we get a value like 5.113 just due to random variation? Our test statistic says, well, it's not that far away, only about a standard deviation. And the p-value says there's a 28.54% chance that if this claim was true, you'd get a value for x bar that far away from the mean. So it seems like this is not that strange of a value to see if HO is true. In that sense, it's kind of consistent with HO being true, and it means it's reasonable that HO is true. And you don't want to reject a claim that has a reasonable chance of being true. You want to save your rejections for when you feel you're convinced beyond a reasonable doubt that you've proven your case. Let's go ahead and have a look at another example. So moving down to part B, again the same scenario. They've done step 1 for us. They've set up H0 and H1. They've decided what level of risk we're willing to take of making a type 1 error, so they've set alpha. They've started to gather the evidence. They just haven't done the weighing, but they have the x bar, the s, and the n, and so we're going to come in and finish that step off. Because this is a test about a mean, we're going to do a t-score, and it's going to be our x bar, 42.503, minus the claimed mean of 31.2, divided by the sample standard deviation, which is the reason we're using a t-score, divided by the square root of the sample size, which is 12. And just a reminder on the calculator, you want parentheses around the top and bottom. But also a quick reminder about why we're doing the t-score in the first place. We're trying to decide, is 42.503 reasonably close to 31.2, because then maybe HO is true, or are these so far apart that it seems very unlikely that HO could be a true claim and we'd still get an X bar like this. And I think it's just worth pointing out that just on a gut feeling level, 42.503 to me feels far away from 31.2. And so I wouldn't be surprised if we get a very big t-score because of that. T-score measures how big of a difference this is, and it just feels to me like a big difference. So let's have a look at that on the calculator and see if it feels that way to the calculator. So parentheses around the top, 42.503 minus 31.2, and the parentheses for the numerator. Now we're dividing, so start the parentheses for the denominator, 4.8677, divided by the square root of 12, and then the parentheses for the root and the denominator. So I think this is a big difference, and the calculator says, yes indeed. Those two values, X bar, 42.503, and the claim mean, 31.2, are 8 standard deviations apart. So you want to think about chapter 8, and we say, you know what, if this is the true mean, we're probably not going to get that for X bar, but we should be close. Well, our X bar did not turn out to be close to 31.2. It's 8 standard deviations away. And so it seems very unlikely that if this was the true mean, we would have landed 8 standard deviations away. So I think that the true mean's within a couple standard deviations of my X bar, and the claim means 8 standard deviations away, so that seems very unlikely that it's the true mean. So I'm leaning very, very strongly towards rejecting that. There is a chance that you could get a value for X bar of 42.503 even if this was true, but I think it's a very small chance. And the step 4, calculating the p-value, is calculating that chance. If HO is true, how likely is it? What's the chance we would have gotten a value for X bar this big? So I'm going to put 0 in the middle, representing the t-score for 31.2. And then for my test statistic, I'm going to put this 8.044. Now, just a reminder, in reality, that's way over here on the edge of the paper, but I'll just show it in the tail. And then this is a right-tailed test based on the greater than symbol in H1. So whatever the area is to the right of my test statistic, that would be my p-value. Now, that looks really small in the picture, but the fact is it's even smaller, because this would probably be a number like 3 or 2.5, so 8 is way out there. And to calculate how small is that area really, we would use the TCDF function. We'd do the left boundary of that shaded area, 8044, the right boundary, which there's not one, so that would be infinity, and then we would put on the DF. And for this one, the DF is n minus 1, n is 12, so we get 12 minus 1, or 11. So I'm going to add that 11 piece to that for the TCDF. So let's bring in the calculator, see how much area is out there. We go into the distribution menu, we choose TCDF, left boundary 8.044, right boundary is infinity, and that's with 11 degrees of freedom. And it looks like a 3 at first, but if you see the E -6 over here, that means that's coming out in scientific notation, so we need to move our decimal 6 spots to the left, or we could say that 3 is going to be in the 6th decimal spot. So that would be 1, 2, 3, 4, 5 zeros, and then we'd have the 3 and the 1. And so there's our p-value, really small number. Now typically, we don't write that many decimals on our p-value. Typically we only go 1, 2, 3, 4 and cut it off right about there. So if I did that and rounded my p-value to the normal 4 decimal places, I'd get that the p-value is essentially or approximately nothing. So that's saying that it's almost impossible that this would be true and you'd get a mean that far away. Well, we did get a mean that far away, so the part I doubt is that this is true. So it seems very unlikely that I would get a value like this if HO is true, but I did get a value like that, so I doubt HO is true. I doubt it very, very strongly, strong enough that I'm going to say reject HO. And anytime I decide to reject HO, there's a risk that's a mistake, that this really was just random variation, and I'm making a type 1 error. but the p-value assesses how big that risk is, and that risk seems very small. So I'm rejecting HO because I feel like there is an acceptably small risk of making a type 1 error. Alright, so that's a couple mechanical examples. Next we'll go ahead and take a look at the procedure in general and then move on to some applications. Alright, let's go ahead and look at the procedure for performing a hypothesis test for mu when sigma is unknown. The requirements we're going to list, but they're essentially the same as what we saw for confidence intervals for the average in Chapter 8. So x bar must be normally distributed in order for us to calculate our p-value. So we must meet at least one of the following conditions. The sample size could be large, and we would define that as n is greater than or equal to 30. Or another thing that would be great is if the population is normally distributed. And another way we could satisfy the requirements is if we had a medium-sized sample from 15 to 30 and the population was not severely skewed. Generally we focus on our sample size, so if I look at those requirements in terms of sample size, if our sample size is large, the requirements are met. If the sample size is medium, then we need a population that's not severely skewed. If our sample size is under 30, we need the middle bullet, which works for any sample size, which would be a normal population. And then the steps for determining or for carrying out the hypothesis test, step 1 would be to determine H0 and H1. And since these are about averages, H0 will start off by saying mu equals something every single time. And then we'll want to decide on our significance level alpha. That's going to be given to you in most problems, so you're just going to need to write it down and think about what it means. And then calculate the test statistic, which will be x bar minus the claim mean divided by the sample standard deviation over the square root of the sample size. And then again, just a reminder, because we're using S, that's why we get a t-score. If somehow we knew sigma, we could use a z-score, but that's not realistic. And we'll always round these to 3 decimal places, just like we did our z-scores. Because it's a t-score, we're going to use t-CDF to determine our p-value instead of using normal CDF. Rejecting or not rejecting will be just like always, comparing the risk of a type 1 error to the risk we're willing to take of making a type 1 error. And then we'll state the conclusion of the test in plain language using the words of the application. So let's go ahead and apply that to an example where we do have an application and we can get all the way to stating our conclusion in words. So it's widely believed that healthcare costs have been rising at an unacceptable rate. In 2005, the average cost of healthcare premiums for an individual with a job-based healthcare plan was $3,991 per year. A news website wants to show that the cost has increased dramatically since then. They obtained a random sample of 60 individuals from the U.S. who have a job-based healthcare plan, and the sample produced an average cost of $5,311 per year with a standard deviation of 11.95. They want us to perform a hypothesis test at the 5% significance level to try and show that the true average cost has increased from the 2005 level. Alright, so this looks like a hypothesis test, so that's going to have 6 steps to it. Step 1 is going to be to determine H0 and H1. And the first part of that would be to think about, is this going to be a test about a mean or a proportion? So we can just look at the wording here, and it says we're trying to show that the true average cost. So since this is a test about an average, I'm going to write mu equals an H0. And then I'm going to try and think about what to set that equal to. And it can be a little tricky. We see several numbers, 2005, 3991, 60, 3511, 1195. So what do we set it equal to? Well, first of all, it's a claim about an average. So this is stated as an average healthcare cost, and so is this one. So it's one of those two. And there's 2 ways that we can figure out which one to use. One of them is we would never use the sample value here. The sample is supposed to come in step 3. It shouldn't even be around when we do step 1 and 2. And if you look at this 5311, it says the sample produced that. So that means that's an X bar right there. So we're going to use that later on our test statistic. So that means the 3991 should be the one. But I want to also show you another way where we can see that's the right number. What we're trying to show is H1, and it says we're trying to show that the true average has increased. So that would be that mu has gone up from what? The 2005 level, and the 2005 level was 3991. So if I write the 3991 right there, then H1 is saying that the mean has increased from the 2005 level, which is a match of what we're trying to show. And H0 and H1 always have the same numbers in them. So if you're having a hard time figuring out what the numbers should be for H0, sometimes you might think about what H1 should say, and if you can figure out the number for H1, it's going to be the same in both spots. Alright, so it looks like we're going to do a right-tailed test then because of the greater than there. So we want to move on to step 2 and write down our significance level, which is given as 5%. So moving that to a decimal, alpha is equal to 0.05. So that's the setup phase. That's supposed to happen before we even collect data. And now we go out in step 3 and we get our sample and we start gathering the information. So part of that is that X bar. X bar is 5311. And then we also have a standard deviation from that same sample. Since it's a sample standard deviation, that would be S, 1195. And we know the size of the sample was 60 individuals, so that tells us that N is equal to 60. So that's the same sort of information they were giving us on the last couple examples we did that were just mechanical. So we can use that to calculate our t-score. So t would be the X bar, 5311, minus the claim mean, 3991, divided by S, 1195, which itself is divided by the square root of the sample size, which is 60. And that'll give us our t-score. So again, reminder, when you go to the calculator, you need parentheses around the top and the bottom. And the other reminder is to think about, does that seem like a big difference or not? So if you think about money and you thought something was going to cost about $3,991 and you found out when you got to say the register that it was $5,311, that seems like a lot more money than you were expecting. So I expect kind of a big t-score here, but let's see how that works out on the calculator. So again, remembering those parentheses around the numerator, so 5311 minus 3991, and then end those parentheses, divide and start new parentheses for the denominator, 1195 divided by the square root of 60, and then end the parentheses. So I thought that was a big difference, and the math is coming out that way. I'm getting 8.556. So a couple things to point out here. One is, it's amazing to me how often people actually mess up this z-score because they forget the parentheses around the denominator. So that's really important. We're used to putting them around the numerator from z-scores back in chapter 3 even, but putting them around the denominator is kind of a new step for us, so you got to remember to do that, otherwise it really changes your answer. And then we want to start thinking about what is this telling us overall in the hypothesis test. It's saying that our sample value is over 8.5 standard deviations away from the claim value. We expect our sample value to be near the truth, or turning that statement around, we expect the truth to be near our sample value. So that makes a value that's 8.5 standard deviations away seem very unlikely to be the true mean. HO claims it is, but in order to continue to believe HO, you have to think that just due to random variation we landed 8.5 standard deviations away, and that seems very unlikely. And again, as soon as I start saying that seems very unlikely, that's a probability statement. So I want to calculate what is the probability that if HO is true, I would land 8.5 standard deviations away. So I draw a bell-shaped curve for our t-distribution. In place of that 3991, I'll put a 0 because we're in the t-score format. And then in place of the 5311, I'll put our test statistic, which is 8.556. Look at what kind of tail test it is. It's right-tailed, so our p-value will be whatever this area to the right is. And that looks really small in the picture, but again, just like on the previous page, it's even smaller because 8.5 wouldn't be right at the edge of the tail. It'd be off the paper probably. So my p-value is whatever that area is, and that area would be a TCDF from 8.556 to infinity with, and then we need a DF. And the DF is one less than the sample size. So the sample size is 60, the DF is 59. So that'll be our DF there, and so let's plug that in and see what the p-value is. So go to the distribution menu, TCDF, from 8.556 to alpha infinity with 59 degrees of freedom. And we get a super small value. E-12 means there's 11 zeros, and then we finally get to that 3, we usually only write 4 decimals on our p-values, so if we did, those would all be zeros. So it looks like our p-value is essentially 0, saying there's basically no chance that if HO was true that we'd get an X bar like we did. But we did get that X bar, so it means there's almost no chance HO is true. And so let's move on to that next phase, which is making our decision. So we're trying to decide whether to reject HO or not. Our leaning, or not our leaning, but our desire should be to reject HO because we're on H1's team. But we're not going to do that no matter what. We're only going to do it if the evidence is strong and the risk of making a mistake is weak. When you get an X bar that is 8.5 standard deviations to the right of the claim value, that is a big difference between the claim value and the sample value. That's very strong evidence against HO. When we weigh the risk that rejecting would be a mistake, it seems like there's almost no risk that rejecting would be a mistake. So we should go ahead and reject HO because the evidence is strong and the risk of making a mistake is very low. And then why did we reject HO? I'm going to talk about it basically in terms of this test statistic and the claims up here. I'm going to say we had enough evidence at the 5% significance level to show, and what were we trying to show? We were trying to show that the true average cost of healthcare has increased from the 2005 level. And I think it'd be good to mention what that level was, which was $3,991. So when I say we have enough evidence, that's based on two things. Based on a big difference between the sample value and the claim value, that's primarily where I get my evidence. I know that's enough because the chance of such a big difference is less than 5%. And that's where the significance level comes in. And then when we talk about what we're trying to show, that's always H1, so we're trying to put H1 back into words, and sometimes your question itself is going to have those words for you to kind of help you write that out. Alright, continuing on with the same problem, they want us to comment on the requirements. So in this one we had a sample size of 60, and I'm going to start off there, and I'm going to say because n was equal to 60, which is greater than or equal to 30, that implies that X bar is normally distributed. And having an X bar that's normally distributed is what's required for a hypothesis test of the mean. So because n is equal to 60, which is bigger than or equal to 30, that implies X bar is normally distributed, and that implies the requirements are met. This is really kind of the simplest case that you can be in when you have the big sample. That's when stating the requirements goes the smoothest. Alright, let's go ahead and take a look at this now from the confidence interval point of view. So let's compute a 90% confidence interval for the true average cost of individual job-based healthcare coverage. Because this problem is about the true average cost, when I go to do my confidence interval, I'm going to want to use the formula X bar for average plus or minus a T star times S over root n as my formula. So I want to start out thinking about the pieces that I have for this already. If we bring in the previous version of the problem, X bar and S and n were things that we calculated already, so I'm just going to copy those over from that paper onto this new one. So we had an X bar that was 5311. We had an S that was 1195, and we had a sample size of 60. So the thing that seems to be missing, we have X bar, S, and N. It seems like the T star is the missing piece. A common mistake people will make is they'll say, oh, we know T already, it's 8.556, we did that in step 3. But what we have to remember is that the star on the t is supposed to be telling us that we need the t-score that goes with 90% confidence. So that t-star is connected to that confidence level. So when we think about what t-score to use, we need to draw a bell-shaped curve in. We need to put 90% area in the middle. That leaves 10% left over, which means 5% on each side. And we need the t-scores, negative and positive t-star, that trap that 90% area in the middle. So there's two ways to do that. One would be to use inverse t, but we don't all have that on our calculator. So the other way is to calculate the df of 59 and then use our t table. When we go to do the t table, we'd look up 0.05 and drop down to 59 degrees of freedom. So here's the 0.05 column, and we can start dropping down, but there is no 59 degrees of freedom. We have a 55 row and we have a 60 row. So we're looking at grabbing one of those two from the 0.05 column, either 1.673 or 1.671. So you might remember our rule from chapter 8 is if you come in between two DFs that are on the chart, we should use the smaller DF. So we're going to use 55, which is the smaller of the two that have this trap, the 55 and the 60. And if I do that, if I go to t of 0.05 and I drop down to the 55 degrees of freedom row, I get a t-star of 1.673. So that's what we're going to use as our t-star when we do this confidence interval calculation. If you use the 60, it's not that big of a difference. If you use inverse normal and use 59, it's not that big of a difference. But this is our official policy if we're going to use the table. So let's see, our x bar is 5311 plus or minus the t-star 1.673 times s, which is 1195, divided by the square root of n, which is 60. So we copy that 5311 again. That was our point estimate, but we have no faith that that's the right answer for this population. So we're going to give ourselves some margin for error. So let's calculate how much margin of error we need. 1.673 times 1195 divided by the square root of 60. And that gives 258.100 and so on. But remember, we're supposed to match decimals with our point estimate, so since this is a whole number, I'm just going to go to the whole number on this one as well and just put plus or minus 258. And then we get our interval by taking the point estimate, 5311, subtracting 258, and adding 258. So our boundaries are 50, 53, and 55, 69. And we're trying to find a confidence interval for the true average, so that means the population average or mean, which should be mu. So we feel like mu is an element of that interval. So in a way this is a weird problem, just kind of review of chapter 8, what's it doing here, but it gives us another way of thinking about why we rejected on the hypothesis test. What we're saying is that when you get a sample mean of 5,311 for the healthcare costs, you don't expect that that's correct for the entire population, because it did, after all, just come from a sample of size 60. But you do expect it to be close to the truth, and the margin of error says you expect it to be within $258 of the truth. So when you go $258 each way, you're making a range that you're pretty confident has the truth in it. So we are confident the true mean is somewhere in this $5,053 to $5,569 range. But if we look back at the original problem that we're doing the hypothesis test on, the claim was that the mean was 3991. That's not in our interval, that's nowhere near our interval. So if we believe this interval, it's hard to believe HO, and that's why we ended up rejecting HO, because it's not consistent with the X bar we got, which makes us believe that the true average is somewhere in the $5,000 range. And I just basically answered this last part. They said to explain how the confidence interval agrees with the results of the interval that we just did. I just noticed this says E. Let's change that to a D, and I believe that this part should say part C. So explain how the confidence interval that we just got here agrees with the results of our decision. So I already said it to you in words. Here's how I would write it in symbols. I would say if mu is an element of that interval that we just computed, 50, 53 to 55, 69, then that implies that HO that states, here let me say it this way, that implies that mu is greater than 3991. And that implies that H0 that stated mu equals 3991 is a false claim. And if we're confident that HO is false, then the right thing to do would be to reject it. So again, kind of saying that more in words, if we think that the mean is somewhere in this range, then the mean can't be 3991. It's bigger, like H1 says. So we should reject HO in favor of H1. All right, and just checking that real quick, that is in fact what we did, is reject HO. So I've shown how the confidence interval would lead to the same decision, and in that sense it agrees with that decision. Okay. Okay, section 9.3, final example. A company produces bags of rice that are labeled as containing 5 pounds of rice. The company routinely performs hypothesis tests on its own product to try to detect if its filling machine is malfunctioning. A recent sample of 12 bags of rice produced the following weights in pounds. And then we have the 12 weights there and a sum of x squared given to verify our data entry later on the calculator. They want us to use the norm test results from the sample data that are shown below to comment on the requirement of the hypothesis test. So when I think about the requirements, usually the first thing I consider is sample size. And our sample size here, if you look through the data and even what they told us there, is only 12 bags. So that's the first thing I would comment on, is say that since the sample size is only n equals 12, I'm concerned about that because that's less than 15. So that puts it into the small size zone. So what we need when our sample size is small is for the population to be normal. So go ahead and list that. We need the population to be normal. Now just because we need it to be normal doesn't mean that it is. So typically what we do on problems like this is we just say that we're hoping for that. But on this problem, they've gone to the computer and they've done a norm test like we did in the Chapter 6 chapter problem. And so we can use that to investigate whether that seems like a reasonable assumption or not for the population to be normal. And so if you remember the steps from Chapter 6, we want to look at the p-value there, and in this case the p-value is 0.550. And then we want to think, is that smaller or greater than 0.05? In this case, 0.550 is greater than 0.05. And what we're checking for here is if our data had come from a normal population, it would have had a certain look to it. And this data doesn't look exactly like that. So we're saying, well, are the differences that we're seeing in this data set from a normal data set small enough so that it's reasonable such difference would occur just due to random variation? And our p-value here is saying yes, there's a good chance of that. So when our p-value is bigger than 0.05, it doesn't prove that our data set's normal, but it looks enough like a normal data set so that we can say the differences between this and what normal data would ideally look like could just be random differences. So again, it's a reasonable assumption that the population is normal. So that doesn't actually mean we have a normal population, but it's a reasonable assumption. So we're not just hoping here, we have a reasonable hope, and so it makes sense to go ahead and proceed with the hypothesis test. So that's what we're going to do next. So let's go ahead and try and perform a hypothesis test at the 5% significance level to determine if the filling machine is, on average, filling the bags with an incorrect amount. So when you see that phrase significance level, that indicates a hypothesis test. Of course, the words hypothesis test indicate that. And when we're going to do a hypothesis test, that's going to be a 6-step process, where step 1 is to determine HO and H1, the null and alternative hypotheses. And when you start out in that step, you want to think about, is this a test about a proportion or an average? And we're trying to determine if the machine is, on average, filling the bags with an incorrect amount. So when a test is about an average, it's going to be a test about mu rather than p. We always have mu equals in the H0, and then either less than or greater or does not equal in H1. So trying to figure out how that's going to go, first of all we think, what should we set mu equal to an HO, and we're trying to see if it's an incorrect amount, so that'll be H1. We should set HO to whatever the correct amount is. So if we go back up here to the original problem, it says that the bags are labeled as containing 5 pounds, so that's what it's supposed to be. That's the company's claim. So that's what we're going to set mu equal to in H0. So our default starting assumption is going to be that the bags are being filled with the right amount on average. And then when we look at what are we trying to show, we're trying to show that no, it's actually an incorrect amount. And an incorrect amount could be underfilled or overfilled. It could be in either direction. So it's not a greater than or a less than. It's the kind of combination of those, which would be that does not equal. Either of those cases would be the ones we're looking for. And then step 2, try and decide on a significance level, but for us that's not a decision, it's just a hunt. Find what the significance level is, and that's right there, 5% significance level. So I'll set alpha equal to 0.05. And then just a reminder, we've already seen the data on this problem, but when you do a hypothesis test, you should go into it with these done before you collect data. So just a reminder, this is called the setup phase of a hypothesis test, where you're determining your HO and H1 and deciding on your significance level. And it actually makes sense in a process like this that they're probably doing tests on this filling machine several times a day, and so they just always have the same setup for H0 and H1. They don't even have to do that for each test. It's just there all along. And then for them, they jump every day right into the gather and weigh process, because again, their steps 1 and 2 would be set up already. So gather and weigh what? Gather and weigh the evidence. In this case, gather and weigh rice, I guess, but in general, we're gathering and weighing the evidence. So this is where steps 3 and 4 come in. And so we'll start off with step 3. This is a test about an average. So our test statistic would be a t-score, and we would take the x bar from the data, subtract the claimed mean from H0, and then divide that by s over root n to see how many standard deviations apart these two things are. And to be able to do this, we need to know x bar, s, and n, and on this problem they were not given. But they did give us data. So if they give us data, we can find those things on our own by entering them into the calculator. So I'm going to go ahead and do that. Let me slide this over a little, make room for the calculator. Alright, so we would want to go into the stat menu and edit and enter this data into L1. So I'm just entering in the weights of those bags of rice. And then once I have all of those entered in, I want to calculate the mean and standard deviation, or more to the point, I want the calculator to do that for me. So I'm going to hit the stat key again, go over to the calc menu, and I want one variable statistics and telling the calculator that my data is in L1. And I want the mean and the standard deviation and the sample size, but actually the first thing I'm going to look at is the sum of the x squareds, 306.5321. It looks like that's a match, and that indicates that I don't have typos in my data. So I can trust the mean and standard deviation that I'm seeing. So let me slide the paper up here, and my x bar is 5.0525. Just a quick mention on rounding rules. Our rounding rules for mean said that you should put at least one decimal place more than the original data, so that would be 3. But if we go 4, we have an exact answer with no rounding error. So at least means 3 or more, and if I can go just one more and eliminate the rounding error, I'll definitely do that. And then S is 0.13451, and we want at least 1, 2, 3, 4, 5 digits on that, and the N was 12. So there's all the pieces we need to plug into our test statistics, so I'll go ahead and start doing that now. So my T would be my x bar, 5.0525, minus the claimed mean of 5. I always like to stop at that point and think, does that seem like a big difference? So on average, in our sample of 12 bags, we were overfilled by about 0.05 ounces. It doesn't strike me as a particularly big difference, but it really depends on the standard deviation. So 13451 is our sample standard deviation, and we divide that by the square root of our sample size, that is 12. And that's the way we would write that, but when we go to the calculator, if there's more than one number in the numerator, which there is, we need parentheses around that. More than one number in the denominator, which there is, then we should put parentheses around that. So those red parentheses don't need to be written down, but they do need to be entered into the calculator. So let me go ahead and bring that back in. In the numerator, we want 5.0525 minus the claim mean of 5, divided by, and then open the parentheses again, 0.13451 divided by the square root of 12. Close the parentheses once for the square root and once for the denominator. And then we want to see, is this such a small difference that it's reasonable that the machine could be working right and this difference was just random variation? Or is this such a big difference that it indicates that something has gone wrong with the process and the mean is actually different than 5? And I don't get a clear answer to that. I get 1.352. If that difference was less than 1 standard deviation, I'd say it could easily be random and I wouldn't reject HO. If it was bigger than 3, I'd say it's very unlikely that difference is due to random variation and I would reject HO. When I get something in between 1 and 3, that's a little bit more of a tougher decision, and I really need to see the p-value to make that answer clear. So let's go ahead and do that. Step 4 would be to calculate our p-value. So I'll draw a bell-shaped curve, which seems reasonable based on these requirements up here. We were checking to see if x bar was bell-shaped or not. And then this is going to be the t-curve, so I'll put 0 in the middle. And with the t-curve, I always like to remind myself of my df. So the df is n minus 1, which would be 12 minus 1, or 11 in this case. And then I'll put my test statistic on that picture, 5.0525. Whoops, my apology. That was the x bar. I want to put my test statistic, which is 1.352 on the picture. And then when you're doing a two-tailed test, not only do you put your test statistic, you put the mirror image on there as well, so that would be negative 1.352. And on a two-tailed test, you don't just find that for your p-value, you also find the other side as well, and you have to add those two areas together or find 1 n times 2 to get your p-value. So in this case, the p-value, or at least the area on the left side, would be TCDF, and then I'd go from negative infinity to negative 1.352 with 11 degrees of freedom. And you could do the area of either side because of the symmetry, they'll both be the same, so it doesn't matter too much which one you do. But I'll go ahead and enter that one into the calculator. So into the distribution menu, down to TCDF, that could be 5 or 6 on your calculator, just pay attention to not the numbers but the words. We want TCDF from negative infinity to negative 1.352 with 11 degrees of freedom. And when I do that, I get 0.1018. But this is a two-tailed test, so to get the p-value, I'm going to take that and double it times 2, and I get 0.2035. So my p-value on this one, let me go ahead and slide this over. So my p-value is approximately 0.2035. Let's go ahead and box that because there's a lot of stuff going on here. And just a quick look at this, by the way. When I wrote the area on one side, I rounded this and I said 1018. And if I took 1018 times 2, I'd get 2036. And that's just because of the rounding error. It's a little bit more accurate to double first and then round, and that gives me the 2035. But I would take either of those, 2035 or 2036, for the p-value. And in either case, we're going to end up making about the same decision. And speaking of that, let's go ahead and bring in the other next page here. We have more space to finish this problem off. And so let's look at what we have. We have a test statistic of 1.352. That was kind of a tough decision as to whether that was a big difference or not. But when we did the p-value, it says there's about a 20% chance of seeing such a big difference if HO is true. And that's a pretty reasonable chance. So that means that HO being true is a reasonable possibility. And I don't like to reject HO if it seems like a reasonable possibility that it's true. So in step 5, I'm going to say do not reject HO. And there's two ways to look at it. One is to say because the difference is small, that's weak evidence against HO, making it look like there's a reasonable possibility that HO is true. There's a 20% chance of seeing a difference this big between the sample value and the truth. So if it really was true, we might have seen a difference like this. It wouldn't have been a surprise. So that makes HO look like a reasonable claim, so I wouldn't reject it. The other way of looking at it is when I'm thinking about rejecting HO, which I want to do in all hypothesis tests because H1 is my side, HO is the one I'm trying to attack. The p-value tells me the risk that rejecting would be a mistake. So if I were to reject HO with the evidence I have on this problem, I'd be taking about a 20% risk of making a type 1 error. And as we look up here, we see we're only willing to take a 5% risk, so that would be too high. Okay, so we're not going to reject HO because that would be a little bit too risky in this case. And now that we've made our decision, we want to state our conclusion in words. So we didn't reject HO, so there is not enough evidence at the 5% significance level to show, and what were we trying to show? We were trying to show H1, and H1 said that the true average amount of rice that's going in these bags is different from 5 pounds. So there's not enough evidence at the 5% significance level to show that the machine is, on average, filling the bags with an incorrect amount. And just one other thing to note here, when I moved on to step 5, that was the final phase of this, which is decisions and conclusions. It's not vital that you label this, but we do a hypothesis test in 3 phases. We have our setup phase, the gather and weigh the evidence phase, and then the phase of coming up with our decisions and stating our conclusion in words. I do think that it's a good idea to number the steps 1, 2, 3, 4, 5, 6 as you go through, just to make sure you're remembering to do everything, that nothing gets forgotten, and that there's a logical flow to your work. Like in the steps like this, things kind of the 3's over here, the 4's over there, it kind of looks right to left instead of left to right, so the numbering kind of helps to show the flow that we should be following as we go through that. Okay, let's go ahead and finish this off with a follow-up question or two. Calculate a 95% confidence interval for the true average amount of rice in the bags. So if they want us to do a 95% confidence interval, then I'm going to want to use, well, first of all, I want to think, is it a mean or proportion? We already talked about that it's for a mean. So for a confidence interval for the mean, I'd want to use the formula x bar plus or minus t star times s over root n. And on the previous page, we used our calculator to get x bar, s, and n. So the only thing we need is the t-score. And again, I mentioned this on the previous section, but it's a little tempting to use this t-score right here, but this t-score has nothing to do with 95% confidence, and the t-star says we need a t-score that matches up with the 95% confidence level. So to get the t, I don't look back at my previous work. I draw a bell-shaped curve for t with a df of 11. Remember, our sample size was 12, so this is 11 minus 1. And I'm trying to find a t-star and a negative t-star that trap this area of 0.95 in the middle. And if we have 95% of our area in the middle, that means that we have 5% left over, and that means 0.025 on each side if we cut that remaining 5% in half. And if the area in our tail is 0.025 and we have 11 degrees of freedom, then we can go to our chart, find the 0.025 column, drop down to 11 degrees of freedom, And there is the t-score we need. T of 0.025 with 11 degrees of freedom is 2.201. And once I fill that in, now I have everything I need to do the confidence interval. We can look back at our work on the previous page and see our x bar. That was 5.0525 plus or minus the t-score that we just found, 2.201. And then that would be times s over the square root of n, which is 12. So we have all the pieces entered in, and now we can go ahead and start doing the calculator work. I always like to see the margin of error calculation, which would be this plus or minus piece. We know that this value right here came from a sample, and therefore is going to have some sampling error in it. So that's very unlikely to be the true value of the mean. We have to give ourselves some margin for error. And so let's see how much on the calculator. 2.201 times 0.13451. And then divide that by the square root of 12. And I get plus or minus 0.0855. Just a reminder on the rounding rules, if we have 1, 2, 3, 4 decimals here, then we should match that with 1, 2, 3, 4 decimals here as well. And then we want to get our interval, so we're going to subtract and add. 5.0525 minus 0.0855. It gives the left boundary of my interval, 4.967. And then we do that again with a plus to get the right side. And just a quick mention and fix here before I go on. We had 4 decimals here and here, so we should actually have 4 decimals here as well. It just happened to be a 0, so the calculator didn't show it, but I should still write that down. And on the plus side, we'd have 5.138. And again, we want 4 decimals there, so I'll add the 0 on that one as well. Alright, so this is our confidence interval for the true mean, so I think that mu is an element of that. And then just quick discussion on how that relates to our hypothesis test. In the hypothesis test, they were claiming that the mean was 5. 5 is in this interval, so everything in this interval is a reasonable possibility for what the true mean might be. 5 is in here, and that means that HO that claims mu equals 5 looks like a reasonable claim, and when HO looks like it's a reasonable claim, we shouldn't reject it, and that's in fact what happened. So all that discussion I just had right there is actually part D. It says explain how that interval we just got right here in part C agrees with our decision to not reject from step 5 of part B. So let me just write that out in symbols. If mu is an element of this interval from 4.9670 to 5.1380, then mu could be anything in that range, and that would be a reasonable possibility. So that means one of the things mu could reasonably be would be 5, and I picked that number in particular because it's the number from HO. If mu could be 5, if that's reasonable, then it means HO that stated that mu equals 5 could be a true claim. And if it looks like it's reasonable that HO could be true, then our decision should be do not reject HO. We want to reject HO only when we're confident it's false, and the claim number from HO is in our interval, making it a reasonable possibility, so when it looks like it's reasonable that HO is true, we shouldn't reject it. And then just quickly checking, make sure that does match up with our decision, because we were trying to show how the interval did agree with the decision that we had back in part B. Alright, that finishes up section 9.3.